Homework Hotline, what is your emergency?
Hey guys, you know what today is?
Tuesday?
Well, it's a good day to get some homework help.
And I bet we can help with that. Is that us?
I think we can. So call us with your science, math, or English questions.
We are live Tuesdays and Wednesday from 4:30 to 5:30 p.m. and you can call us at the number on the screen. It's right. Whoop, not above me anymore.
Oh, it's changed. It's above me now.
Yeah.
So easy.
720-424-1666.
And for our live broadcast, you can tune in a variety of ways. You can tune into Comcast Channel 22 or 882 if you want to check us out in high definition. There's also Prism TV, Channel 8007, or you can go to livestream.com, click on Discover, and put DPS TV in the search box. And last, we're also live on Facebook at EG Homework.
Yeah, and if you want to watch some of our past shows or segments, you can go to YouTube and find us at Denver DPS TV.
So are you wondering why we have a couple of logos on the bottoms of our screen down there? Well, that's because Homework Hotline is sponsored by Emily Griffith High School, where Nathan and I teach, and by Contemporary Learning Academy, where Sam teaches.
And we also have a guest today. We have Molly Nuanes from the Museum of Contemporary Art.
Yeah, and they have a lot of great programs for creative teens, so we'll hear more about that in a half an hour.
So how did the artist solve the mystery?
What mystery?
By drawing conclusions.
The real question.
Nice.
Like my joke? All right, so we love phone calls, but we also will take questions through social media. Derek, can you tell us a little bit about that?
Sure can. I'm Derek. I'm an intern here at DPS TV. Like Becca said, I grab all the questions from social media and get them over to the teachers. I'm also the trivia master. I'll ask a question at the beginning here at the show, and then throughout the show we want to hear from you guys, get an answer. Today's question, we have a culinary question. The question is, what are the 2 top-selling spices in the world?
All right, well, if you think you have an answer to that, or even just a guess, we like guesses too, you can give us a call at that number on the top of your screen. Let's also give you the contact information to get your questions in through social media. You can get us through Facebook or Twitter at EG Homework. You can text us at 970-680-3771, or you can email us at homework@emilygriffith.edu. So those are all the different ways that you can send your questions to us and we can help you out. So let's go back to Derek at social media and get some of your questions answered.
All right, well, first question is a math question. It says, what is 0.12 times 10 to the negative 3 power as a decimal?
Okay. I can do that. Just leave that up there for a second, Derek. Why? Times 10 to the negative 3rd power.
Correct.
Cool. Okay. Go to my screen. I can help you out. All right. So this is a number that is written. It's close to scientific notation. It's actually technically not, but close to scientific notation. And I'm going to talk about a little concept before I actually explain how and why this is. Well, I'll explain why this is done before I explain how it's done. So when we multiply something by 10, how many, Nathan and Sam, how many of you have you guys heard, when you multiply something by 10, just add a 0?
Yeah, that's
For that
definitely.
many a time. That's the simple way to explain it, right?
It's a simple way to explain it. It's not necessarily true, but it is. It's a simple way to explain it. I remember my elementary school teacher saying that. So if I did 12 times 0, or 12 times 10, I'd get 12 with a 0 on the end, right? Or if I did 3 times 10, I'm going to get 3 with a 0 on the end, which is technically not true. It is an easy way to explain it. And the reason why I say that is because let's say we do 3.0 times 10, which you know what? 3.0, same as 3. If I just do 3.0 with a 0 on the end, that's not true. That's not a true fact. And so what's really happening when you're multiplying something by 10 is not that you're adding a 0 on the end, but that you're moving your decimal point over a place value. So what's happening here is this 3, it's really like 3.0. That is the same thing. And what's happening to get 30, or when we're multiplying by 10, is that our decimal is moving over a place value, giving us 30 when we multiply by 10. So when you multiply by 10 once, we move our decimal point over once. You might have also heard, all right, when you multiply by 100, add 2 zeros. Well, it's not, again, that we're adding 2 zeros, it's that we are taking our decimal spot on this 3 and we're moving it over to the right 2 spots to give us 300. Now, the same goes, and maybe, actually, let me explain this a little bit more, is so multiplying by 100 would be the same thing as multiplying by 10 twice, which again is why I'm moving my decimal over 2 times. Now, the problem that we're seeing up here is actually with negative exponents. Now, when you're doing a negative exponent, what you're doing is dividing. So if I said I was taking something times 10 to the negative 1 power, really what I'm doing is that I'm dividing it by 10 once. Think of division as the opposite of multiplication, which is why. If I'm taking something times 10 to the negative 2, what that really means is that I'm dividing it by 10 2 times. So when I mentioned that if I multiply something by 10, I move the decimal over to the right. If I divide something by 10, I move my decimal over to the left. And so when I'm looking at this problem here, what this is really saying is that I'm taking 0.12 and I'm dividing it by 10 3 times. Which means what I'm going to end up doing is I'm going to take my decimal and I'm going to move it to the left 3 times. Now, if there's no placeholders here, just like I did earlier, we just write a 0. So if I do 0.12 times 10 to the negative third, I end up getting point. I've got these 3 zeros here. 1, 2. And that's why. So I could have answered that, I guess, pretty quickly, but I wanted to explain why that happens. And then that way maybe it might make a little bit more sense as to like when you see any other problem like that, how to actually do it. So hopefully that helped. All right, let's go back to Derek and get some more of your homework questions answered.
Let's do it. All right, so we have a science question that says, where do ultra high energy particles come from?
Yeah. Okay, so ultra high energy particles are, what we're talking about here is like really small particles, like the nucleus of a very simple atom, like perhaps a helium nucleus or hydrogen nucleus, being fired at a very high speed. So these things typically get up to like the speed of light. And the truth is that we don't know exactly where ultra high energy particles come from. Another name for ultra high energy particles is cosmic rays. So it's been observed that equipment that goes out beyond Earth's atmosphere, beyond Earth's magnetic field, or astronauts that have to go out beyond Earth's magnetic field, like say go to the moon, experience a degree of radiation higher than people that live on the Earth. Thanks to Earth's magnetic field, cosmic rays that are all around us in the universe, 99.9% of them are actually blocked from arriving onto the surface of the Earth, thanks to Earth's magnetic field. But if it weren't for that, we would be exposed all the time to these really, again, high energy particles that are, again, just these small particles that are being shot really, really fast. And the concern there is that being exposed to ultra high energy particles like that over long periods of time can increase the risk of fatal cancers. So, for example, maybe if we jump to my screen really quickly, I'll just show a quick image here. So one place that we know high energy particles come from is the sun. although solar high energy particles are not as high energy as other cosmic rays that we've seen. So we know that stars like the sun are capable of jettisoning off high energy particles that certainly can cause damage to living organisms that aren't protected by a terrestrial magnetic field. And you can see in this drawing just sort of this simple diagram, the blue lines surrounding this ball here represent Earth's magnetic field, and you can see that they effectively block or deflect most solar energy particles that come at us from the sun. But again, it's been observed, there was a time when scientists thought that the best explanation for where ultra high energy particles come from would be supernovas. So supernova is the explosion of a very large star. If that were the case, we would expect that cosmic rays or these high energy particles would come from specific locations in the universe, like we would see concentrations of them in different places, and we would expect high concentrations of them in areas where there had recently been supernovas. But when we look around and try to observe for high energy particles, what scientists find is that cosmic rays like this come at us from all different parts of the universe in seemingly equal concentration. So there's not one particular area where we're receiving more cosmic rays than another. So that creates this really interesting question of where could these things be coming from, and what could be producing cosmic rays on a scale that they travel sort of uniformly around us in the universe. But again, so we don't really know where they come from. We think that they likely come from very intense star activity. There may be interactions with other space objects that you might find, like nebulae or black holes. But ultimately what we're talking about here is just the nucleus of an atom being shot at super high speeds. And just as a last wrap up, we're getting closer and closer to talking about sending humans to Mars and perhaps beyond. I think it's likely that within my lifetime there will be one, if not more, missions to Mars. There's certainly one planned within the next decade. And when we talk about sending people to Mars, we talk about having human beings out exposed to cosmic rays for long periods of time. And there's this measurement scale called the Sievert scale that talks about how much radiation a person can be exposed to safely. So they say that if you're exposed to like 1 sievert of radiation, you have an increased chance of getting cancer, and that increased chance is about an increase of 5% that you're going to have a deadly cancer. We here on Earth experience like 0.00001 sievert in a given day, again because our magnetic field, the magnetic field of our planet, blocks us from cosmic rays. But a person who is traveling even at the shortest distance to Mars and back, the quickest possible trip, would be exposed to at least a half sievert. So that would be like an increase of 2.5% chance that they would contract or develop a deadly cancer. And so you can imagine this compounds, if we talk about having people live for long periods of time outside of Earth's atmosphere and magnetic field. So, you know, we talk about sometimes putting people on the moon, people living on the moon, or people living on Mars. And if you have a person that's exposed to cosmic rays for long periods of time, the chances that they're going to develop deadly cancers really increases. And so that brings up the idea that if we are going to have people live in space in the future, we're going to have to think about creating living spaces that are protected from cosmic rays, perhaps that are buried underground. So anyways, just a little side note there.
Interesting to think about.
Indeed.
How that'll go.
Mm-hmm.
All right. Derek, do we have more questions?
We sure do. I got a math question here for you. It says in the figure below, triangle OAB has an area of 72 and triangle ODC has an area of 288. Find X and Y.
All right, that looks like geometry because there's a picture
have it.
drawn.
You can
so
have it.
I'm going to take this one. And, you know, glancing at this at first, I'm going to make a couple of assumptions about kind of what you know. Otherwise, this show could take, or this problem could take the rest of the show, kind of explain everything. What you're going to see in here is some right triangles. You're going to see some similar triangles. And then you're going to see some other algebraic equations that we have to assume and make on the way. So again, I'm not going to go into like what similar triangles are. If you're getting a problem like this, it's fairly challenging. I'm going to go ahead and assume that you are comfortable with similar triangles. And I will talk about how we know they're similar, but again, not going to go into like the details of it. So you kind of notice that there's a circle drawn here. When I'm looking at this and I try to kind of work out the steps in my head, I don't really think that circle is that important, but maybe I'll be surprised as we go. So right here, it says in the figure below, triangle OAB has an area of 72, and ODC has an area of 288. So let's just take a look at what they're giving us first. We have OAB, which is this little guy right here, and this has an area, and I'm going to write this off to the side. And again, I like to do this little subscript here, area of OAB equals 72. And then we have this bigger triangle here, ODC, which still starts with the same thing. And this is really important that they kind of share this vertex, ODC, which is here. Something like this that has an area of, what do we say, 288. Someone say area of ODC equals 288. And again, I have to point this out a lot. The OAB and the ODC, remember that subscript is just because we're talking about area for both figures, and we need a way to differentiate between, are we talking about OAB or are we talking about ODC? Okay, so here's one thing that you might notice. We're talking about area. So my first thought is area equals 1/2 the base times the height. And if you think about area, or if you think about the height of a triangle, we always have to kind of go straight down. Let me just sketch a quick example. If you had a triangle like this that I sketched, right, our area is going to it's not going to be this kind of slanted length right here. Oh. It's not going to be this slanted length, right, because nobody measures at an angle like that. It's going to be straight down. Think about like from the very top, straight down, and it's got to be perpendicular. So when you look at this, you probably notice two things. One, neither of these triangles are completed. And two, you don't see anything in there that like indicates a height. So I'm going to erase some of this because there is something that we are allowed to do. And in geometry, this always seems a little like, I guess, kind of off-putting at first, because in geometry, your teacher hopefully emphasizes over and over again, you cannot make assumptions, which makes it feel weird to kind of draw something and say, this is what I drew. But we can do that as long as we make that statement. And I'll give you an example of what I mean here. Like if I'm looking at OAB, so I'm going to work with that first. Triangle OAB has an area that's 1/2 the base times the height. So we know the base length is right here, that is 18. The question is, what is the height, and how are we going to use that? And we'll kind of get to how we're going to use it in a bit. So the height here, we can actually draw it ourselves, and we can make this a right angle. Right? We are allowed to do that because what we're saying is what I drew is perpendicular. It does represent the height, and I labeled it, and I'm using it that way. So we are allowed to do that. And so we know OAB has an area of 72. 72 equals 1/2. We know the base is 18 because that was, that was given to us. But we don't know the height. And right now, if you're watching, you might be thinking, what are we going to use the height for? And I will get to that. Trust me, that's important information. So we go and we solve this from here, and we say 72 equals 1/2 of 18, which is 9h, and then h equals 8. So again, I just want to point out one more time, like I am kind of rushing through some of this stuff that we usually spend more time on the steps for solving, but I'm assuming that you're comfortable with that. And so if you're not, feel free to give us a call, and I'm happy to kind of walk through any of that a little bit more in detail. The next thing we were looking at is the area of ODC. So I'll do that in green. It's still going to be 1/2 the base times the height. And now we know the area is 288. Now, the problem with this is we don't know the base, and we don't know the height. So again, I'm kind of working through my process here of how I would do this, and part of that is realizing as you start solving, as you're trying to work through these geometry problems, is realizing what information that you don't have, and then thinking about how you can figure that out. So what I'm going to do is complete this triangle, like I already had and erased for some reason. And I'm going to say I don't know the base, right? I know that I've got a base here. If you think about like this big triangle, big green triangle, I've got a base here, and I know part of it's 18, and I know the other part is y, so if that were a number, I would add it. If it's a letter, I can still add it, and that's what I know. But again, we don't know how to figure that out. Okay, we do know that the height of this little triangle is 8. Now, here's where we get to the similar triangles, and again, that's why I say it's kind of, you got to go back and forth a lot. This happens a lot in geometry. So what you should remember, let me erase this. What you should remember is similar triangles. You know two triangles are similar if you have two angles that are the same. All right, so if I have a triangle like this, and then I have a bigger one, and it looks similar, if any two of the angles are exactly the same measurement, like this, and maybe like these two, then I know that these triangles are similar, and what that should tell you is that they have similar proportions to each other. So when we look at this, it's not automatically clear that these are similar, but you do have two angles that are the same. So if you think about this little triangle, let me color it in yellow so it's more easy to see. Actually, that is not easier to see. Yellow is a bad color on top of yellow. So this little green triangle, it has two angles. It has this right angle here. Hopefully you can see with that notation or that label there. And then it's got this little angle right here. Hopefully that's big enough. Let me draw a big arrow pointing to the one I'm talking about. You kind of see that I marked it right here. And now the question is, how do you know that it's the same as another angle? Well, think about this big green triangle right here, right? Part of it, one of the vertices, is this angle again. So just follow the black arrow, and you kind of see that that big triangle has that exact same angle. So this is going to help us, because now we know, now we have kind of some proportions that we can set up because we know these two are similar. So what you should remember from proportional figures and polygons, and especially triangles in this case, is they have the same proportion. What that means is if one side of a triangle, of a bigger triangle, is double the size of the other triangle, then every single side is double the size. So we can use that, and we can say that we can pick whatever we want really, but what we kind of need here is this height right here. So that's what I'm going to solve for, because that's what kind of got me stuck before. So what I'm going to do is I'm going to say, okay, let me highlight in blue, 18 to this entire side, which we said was 8 plus y. So think about 18 as that side length of the little triangle, and it should be 18 plus y, not 8 plus y. And 18 plus y is that same side, corresponding side on the big triangle. So we can set up proportions, and the good thing is we talk about proportions a lot on this show. And we can say 18, so the side of the little triangle, the proportion to the big triangle, which was 18 plus y, should be the same proportion or equal to the height of the little triangle divided by the height of the big triangle, which is h. And now that I'm looking at this, we still don't have enough information, right? Because we have all these variables. So let's think about how else we can do this. And I might have to think about this for a second now. And this is what's so fun about geometry. Like I'm missing something here.
It is, it's a puzzle.
So what I'm trying to think about now is what's a way that I can relate all of these kind of pieces here. Oh, wait a minute.
Radius?
You know what? I'm overthinking this. I could have done, nope. Oh, we do need a radius, don't we?
Or you could do a diameter or a radius, possibly?
Diameter or a radius, if we knew, well, we don't have any other
because
information
you know
about
that's
that.
16, that little bit is 16. So you could find you could do Pythagorean to find the diameter.
Wait 1 second, 18 to 8 is 16. Oh, you know what, let me take a step back.
Yeah.
I got it, actually. I was thinking about the wrong proportions. We don't know h, so that's a problem, right? But we can find x using this. Instead of saying 18 to, we can actually say 18 to, nope, that's not going to work either. What were you saying?
You don't know y at all,
I don't know y.
and you don't know h,
Right.
and you don't know x.
I mean, I could do 18 plus y squared plus 18 plus x squared, or plus h squared, but I don't know h.
Right. Find x and y. Could you find so you know that oh no, you don't know the area of the circle.
Oh, well, we could do actually, nope, because it's that h is kind of messing us up.
Yeah. Okay.
Oh, you know what I forgot about? We know the area. Nope, that doesn't help us, right? Because we still don't know the height. I was going to say we know the area of the big triangle, but we still have that variable in the bottom.
I have to play around with it on paper.
Yeah, how about we do this? I'm going to maybe stop here for a second because I actually have to think about this. And a lot of these more challenging geometry problems, this is kind of the process. I just don't want to spend 10 minutes kind of walking
here
through my
playing,
thought
right.
process, right? So I'm going to think about this, and actually I think we're going to go on break right now. Is that right? Mm-hmm. And then when we come back, we're going to have a guest, and then after that, we'll come back to this problem.
Perfect.
I just probably need a couple minutes to think this through a little bit.
Yeah.
So good problem.
Okay. Well, we'll see you guys in Hi, welcome back. We're here with Molly Nuanes from the Museum of Contemporary Art. Welcome to the show.
Thank you.
So first, tell us, what is your job title and what do you do for the Museum of Contemporary Art?
Sure. So I'm the manager of programs. Am I plugged in here?
I think you don't have any sound.
Uh-oh.
That's what I'm hearing.
Can you guys hear me?
I can hear you, but
Yeah.
that doesn't help.
Our viewers won't be able to. Are you plugged in?
So we're having a little bit of technical difficulty, so give us 1 second.
Well, we want to make sure we can hear her. So
Yeah.
Yeah.
Maybe
All
you
right.
can speak, and then I can just speak
Just
what
repeat
you say.
everything that-
Sure,
Right,
sure.
It'll look
translate
like you're
for you
talking.
or something.
Okay.
Just
Okay.
translate.
Should be all right now, I think.
Okay.
Okay.
So I
Okay.
am the manager of programs, and I work only on our teen programming at MCA Denver. So I run internship programs, I plan events and programs, and it's all for teens.
Oh, okay. So, first off, how would you briefly describe just contemporary art in general, just so our viewers know
Yeah, because
what contemporary art is?
I actually was just told that modern and contemporary are different, and I thought modern art was like the stuff that's done now, which I'm hearing is
Yeah,
not.
no, they are different. There's lots of debate about the deadline of when modern art ends and when contemporary art begins, but typically we like to say it's the art of our time. So artists who are living and working today, making art, sharing it with people.
Gotcha. Good definition.
In like 20 years, what they're making in 20 years, is that going to be contemporary when we have a new name?
If they're
for the
still
stuff that's going
making
on
it, I don't know, maybe by then we'll be at post contemporary art, I'm not sure.
Post-contemporary.
Keep adding post to it, and
I
you're
can't
good.
wait for post contemporary.
Oh, yeah. I'm excited for that. I wonder what that'll look like. So you said you work and do programs for teens.
Yeah.
Tell us a little bit about some of the programs that you have there for teens.
Sure. So I'll back up and I'll say first that we are always free for teens every day, all the time.
Ooh.
So anyone who's 18 and under can always come to the museum all the time. They can see exhibitions or they can come to our programs. So some of the things that I do include an intensive internship program called Failure Lab. That's for 12 high school students per year. They meet with me every single Wednesday from 4 to 6 at the museum in our dedicated teen space, and they plan programs and events for their peers at the museum. So in the fall, we plan an annual teen art show. They also work in intensive workshops with artists. So 2 to 3 times per year, they'll work in like a 6 to 9 week workshop with an individual artist or creative and develop some sort of exhibition in conjunction with that
Cool.
artist. Yeah.
So why is it called the Failure Lab?
That's a great question. I get asked that all the time. So we actually believe that failure is a tool for creativity, and that in order to create anything new or original or authentic, you have to be willing to risk failure in the pursuit of that.
I love that. I absolutely love that.
Yeah.
I think that works with math too. I mean,
Totally.
Yeah, you have to fail a lot of times to actually learn anything. Right?
Yeah,
Yes,
it's
yes,
so true.
exactly.
I like that. I like the name.
Thank you.
So that's one of your teen programs.
Yes.
What else do you guys have going?
So we've got tons of stuff. On Saturdays during the school year, we have a drop-in program for teens called Wake and Make from 11 a.m. to 1 p.m. And you can come up to our teen lounge, and each week has a different theme. So you can make something and do something. Last week we made buttons, like pin buttons, and played vintage Nintendo. And there's breakfast food.
That sounds awesome.
Yeah,
Yeah.
all
That
those
sounds
things
really
are
awesome.
good.
Show up to
Yeah. And then we do a lot of big events periodically throughout the year. So actually this Saturday on the 15th, we have a teen pop-up shop that has been planned by Failure Lab. So we have 5 teen vendors who will be selling their arts and crafts. My students will be selling stuff as well. There'll be music and things to do. So that's on this Saturday from 11 a.m. to 3 p.m.
Okay.
And then at the end of this month, we have a big event called the Failure Fair, which is a part of our college scholarship program. But this day is sort of a creative careers festival. So we want to expose students to the idea that there's a big range of creative careers, that you don't have to just be a doctor or a lawyer or an engineer or a starving artist. If you appreciate creativity and creative things, there's a big spectrum of what you can do. So we'll have tours and talks and drop-in workshops and all kinds of stuff. And then we'll do the award ceremony for the scholarship. And then in the evening, we'll do a teen music night. So we'll have 4 teen bands playing in the basement of our museum.
Cool.
That was
That is
so
really cool.
cool.
Yeah.
That was so cool. So if you are, how do you get involved? If you are a teenager and you're like, I'm just so creative and this is busting out of me, I just need to do something, like how do you get involved?
That's a great question. So our 2 intensive internship programs require an application. So we actually have the applications open right now for Failure Lab for next school year, so 2017, 2018. And you can apply on our website. We also have our Teen Ambassador program, which you can apply for later in the summer. That's a 1-semester program, and they plan a lot of events for the museum as well. And that one is a little bit different because if students in that program meet all of their hours, then they are given a $300 stipend at the end of the semester. So it's more like
Oh.
a job.
So,
Cool.
Can I ask you
Yeah.
this then? Like, so you said there's only 12
12,
students?
yes, for both of those programs per year.
Okay.
For ambassadors, it's 12 per semester. So really it's about 36. But all of our events, like I said, admission is always free, same for our events. So if you ever wanted to drop into a teen event, it's always free.
So just if anybody's out there kind of curious about this, what do you look for in an applicant? Like, what do you
Oh, that's a
consider
great
like a
question.
strong applicant for your program?
So while we're an art museum, we do not require anyone to be a visual artist. We want 2 things. One is that we want you to appreciate creativity broadly and have an appreciation for contemporary art. And that's
Okay.
it. So we have students who do fashion design, students who do graphic design, animation, people who just like art but don't make it themselves. That's really what we're looking for, and people who want to be involved in the museum.
Oh, cool.
I like that they plan things. That's pretty cool.
Yeah.
Like that they have a hand in it, and it's not the adults planning everything. It's the teenagers that
They
get to do it.
They have to, because we've learned that if I plan an event, teens know right away that I planned it. It's very transparent. So it has to come from them to be authentic.
Oh yeah. No, that makes a lot of sense.
Yeah.
That's so
Is-
cool.
Is there anywhere outside of the Museum of Contemporary Art that we could see some of these kind of young artists, their work?
That's a really good question. I don't know. None of our students make work specifically for us that they also show outside. Any work that is done at the museum, we tend to put in our exhibitions, and
Okay.
then they take it home. Yeah.
Okay.
But they get to be in the exhibitions too. That's so cool.
Yeah, so we have a dedicated space up on our 3rd floor that we call the Teen Lounge, and that's where we put all of our exhibitions.
So you could go visit the Teen Lounge then if you wanted to see some of the
Good.
art on display.
You could, yeah. We don't have anything up now, but we will soon.
Cool.
Could I play some old Nintendo?
If you come on Saturday morning.
That was so much fun. Oh,
Yeah.
that was a lot of fun.
I guess I was curious. I'm super jealous of all the things that teenagers get to do now,
Sure.
and that I don't get to. But what kind of stuff could I do if I came to the museum? What kind of exhibits do you have
Oh, yeah.
going
Yeah.
on right now?
So we're a non-collecting museum, which means that we don't have a permanent collection of artworks, which is great because we rotate our exhibitions about 3 to 4 times per year, and we have 3 floors of exhibition space. So right now on view, we have 3 exhibitions that fit really nicely together. In our basement gallery, we have an exhibition called Wall Writers, and it's about the origins of graffiti in New York and Philadelphia in the
Cool.
late 60s and 70s into the early 80s, which is really interesting. So graffiti artists were called writers. They didn't call themselves graffiti artists, so that's why it's called Wall Writers. Up on our first floor, we have an exhibition called Basquiat Before Basquiat. And he's a pretty well-known artist, Jean-Michel Basquiat. Rappers rap about him. His imagery is kind of everywhere. It's been on Nike shoes. It's been on makeup. He's sort of a big figure in the modern contemporary art world. But this exhibition explores a year of his life that really hasn't been studied when he was about 18, 19 years old, living in his first apartment in New York City, and he was too poor to buy art supplies, so he made art on everything. He would bring in tires and doors, and he'd paint on his floors and walls and refrigerator doors. And this really tracks how this early period of his life impacted the rest of his art making, which is really cool. And then lastly, on the second floor, we have an exhibition called Ryan McGinley, The Kids Are All Right. Ryan is an artist based in New York. He's a photographer, and this explores the period of his life from about 1998 to about 2003, when he was a college student at Parsons in New York City. And he carried cameras on him everywhere, and he captured his life and his friend's life, and really that period of time of living in New York City and making it as an artist, which is great.
Very cool. Those all sound really great.
Yeah, you should come check them out.
Do you have any field trips or anything, like if I wanted to bring a group of students to you, like what do you guys have?
Yeah,
in
so
regards to that?
we offer school tours. So teachers can come bring students in groups, and we can do guided tours. You can do a self-guided tour. It's super easy to go online and book tours from our website.
Okay, cool.
And where are you guys located at? Is
Great
it close there,
question.
or-
We're downtown, so we're in Lodo. We're on the corner of 14th and Delgany. And what's really great is that we're 2 blocks from Union Station, so it's super easy to get there.
It has that big, is it a big heart?
Yes,
Okay, I
Yes.
walked by that a whole lot.
the big light up heart sculpture, and it spins around.
What is that? It's a heart, or what is it?
It's made by 2 artists named Sue Webster and Tim Noble. The piece is called Toxic Schizophrenia. And it's a heart with an arrow coming through it and blood dripping out. It's very dramatic. But at night it lights up and it spins around, and it's super cool.
Yeah, I always noticed that and wondered about that. That's
Now
really
you
cool. Now I know. Now I know. All right, well, we have to say goodbye. I think we're out of time.
Okay.
But thank you so much for sharing everything.
Thanks for having me.
Really, if you are a teenager and you are into art, I'm glad I know this now, because I'm going to be sharing with my students a whole
great.
lot now, because I have a lot of students that are into art, not necessarily math, sadly. But I will definitely be sharing it with you. So if you are interested, go on their website and look all of that stuff up, because they've got a lot going on. All right, and that website's right down there. Cool.
Yes.
And we'll see you in a minute. We're going to take a break. Hi, welcome back. Hopefully you enjoyed learning about the Museum of Contemporary Art and all of the programs for teens that they have to offer. We are going to go back and check in with Derek and get the trivia question one more time to get you a chance to answer that and win some prizes. Derek, what is our trivia question?
So the question again is, what are the 2 top-selling spices in the world?
Spices. Okay. Well, if you think you have an answer to that, then give us a call. Let's also give you our contact information just in case you're just tuning in with us right now. You can get us on Facebook or Twitter at EG Homework. You can text us at 970-680-3771 or email us at homework@emilygriffith.edu. So send in your trivia answer or some more homework questions. We can try to help you out. All right, Derek, what do we got going on social media?
All right, so we got a science question that's kind of funny, but it's a very good question. So it says, my science teacher today was talking about the origin of nipples in regards to fetuses. Is it true that the reason everyone has nipples is because all babies in the womb start out as a female?
Yeah, it is true that all babies in the womb start out identical. Males and females start out identical, I guess I would say. And so there's no distinct direction. Yeah, so men having nipples is one of these really interesting things, right? There's no specific purpose for male nipples, and so that sort of leads us to feel like, so I think in biology, there's a couple ways we might try to explain this. If we look at an animal and we see a structure on that animal that doesn't quite make sense or doesn't seem to have a use, we tend to think about, okay, well, what might have been its use in the past? Maybe there was a past where there was a use. An example of this would be the human appendix. So you guys may know we have a little sac-like organ inside of our bodies called the appendix. And that largely the appendix is considered to be non-useful, to have no real function in the body. It's believed that the appendix historically or a long time ago, that appendixes in early humans or proto-humans would have been larger and would have been a storage space for a lot of different kinds of bacteria that would have helped to digest certain kinds of foods that might have been harder for early man to digest. So, for example, there's lots of different chemicals in plants that we have a hard time as humans digesting. We tend to cook the plants that we eat or eat plants that are easier for our systems to digest. But as a human, I can't just go walk out in the forest and eat any leaves that I want or munch on any grass that I want. A lot of that stuff would be difficult to digest. However, in the past, there were humans that probably did have an ability to digest these things thanks to additional bacteria from the appendix. And the notion goes that today we have these small remnant appendixes that might even still contribute some positive bacteria and play a small role in our digestive system, but which are largely obsolete. But then thinking back about male nipples, that's not really the case. There was an argument, I think there is an argument that's been made, maybe there's some people that still defend it, that maybe there was a time when males did nurse babies or something like that. And that has never been proven. There's no real reason to believe that, but that's just an idea that was thrown out there. It is interesting, though, that you have males that develop, and they develop with these additional structures. You know, in development, that's going to be additional energy for a mother to have a baby that's developing a structure that they don't need. So it kind of is a bit of a mystery. I thought I'd also just show, if we could take a look really quickly at my screen. So I've just got a breakdown that shows the anatomy of a male breast. And actually, let me flip over and let's just look at the side view of a female breast. So one of the important things that you see besides muscle tissue down beneath and then adipose tissue, which kind of creates a cushioning layer, what you see here are these lobules and ducts, which serve as the pathway for mother's milk to travel to the nipple so that the baby can drink it. And really interestingly, if you look at this diagram of the anatomy of a male breast, and you can't see it perfectly here, but you can see the label here indicates that there are ducts still. It's something that is kind of funny. Male nipples do have ducts, as if they could conduct some sort of a fluid in that direction. And so I just wanted to lastly point out that all humans, male and female, we have the same 23 chromosomes with this one exception. So we have 23 pairs of chromosomes as humans. So 46 total chromosomes, 23 pairs. And in any given one of us, those pairs are essentially identical. Like Nate and I are very different people. We look very different, but our first pair of chromosomes contain the same set of genes. So like if there's a gene in there, let's say, that codes for eye color, Nate and I both have those genes that code for eye color, but they might code differently. I have blue eyes and Nate has brown eyes. But looking here at the 23rd pair, you can see that females have 2 X chromosomes and males have 1 X and 1 Y chromosome. And it's actually the Y chromosome that contains all of the genetic information that differentiates a male from a female. And so in the development of humans, one of the things that we know is that up until about day 60 in the development of the embryo or of the fetus, the genetic material from the Y chromosome is not referenced. And so there isn't any development from the male side up until day 60. And we know that at that point, then we start to see the development of male genitals as opposed to female genitals. But even before that time, the development of the breast starts. And so that's the reason that males have nipples when females do not. Just as a side note, even though male fetuses start to differentiate themselves from female fetuses at about day 60, doctors are unable to tell the sex of a baby until, like, I don't know the exact time, but it's further than that. It's something like 5 months, 4 months, 5 months. And they're able to do it by looking at the angle between the spinal cord and the genitalia of the fetus. So there's a different angle depending on whether we're talking about a female genitalia or a male genitalia. And if the baby is oriented correctly, a doctor can use an ultrasound to determine whether we're looking at a male or female baby. But the differentiation actually starts before that time.
That's really interesting.
Yeah.
A lot of stuff I didn't know.
Oh yeah, lots of good stuff. Male nipples.
We should actually probably go back to that other question that I didn't finish.
Oh
yeah. Let's
we
go to-
should probably go back to that other question.
And just for continuity, here's the good thing about the fact that this show is recorded and on YouTube.
Indeed.
What you can do is figure out what the time is now. The time is when I couldn't figure it out, and then just splice out the middle, and it'll seem like I just went one further explanation. All right, so I want to throw one thing out there. Sometimes, especially with these geometry problems or these like more complicated, there's a lot of moving parts to it. Sometimes it's very easy to get kind of stuck on one track. Like in my head, I was thinking we're going to use some Pythagorean theorem, and we're going to use proportions with the side lengths. And then I got thrown off, and it was really hard for me to like think outside of that. And we went to break. Sam said, "Aren't the areas proportional?" I was like, "Oh yeah, obviously. I teach this. I know that." Believe it or not.
But it's funny when you have all the information, or when you're the expert, it can be easy to overlook. You're looking for all the possibilities.
Right.
Right.
So that the correct possibility sometimes isn't obvious.
Yes.
Exactly. So Sam, thanks for that.
No worries.
And now my pen doesn't work.
Perfect.
Fantastic. All right, so let's go back to a question for Becca really quick.
All right.
Let's see if
So
this will-
Derek, let's. I guess we're gonna answer
right.
another one of your questions, and then we'll go back to Nathan.
I do know the answer. I'm not faking it. All right, it doesn't work.
Are you sure?
He doesn't know.
All right. Well, we'll get another question answered in the meantime while you get your computer to work.
All right. So we got a question that says, simplify the algebraic expression -2 and then parentheses x minus 3 plus 4 parentheses -2x plus 8.
-2x plus 8. Okay. I got you, and I just have to simplify. All right. So I guess I will talk a little bit about the background of what this means when you see these parentheses like this. So I'm just going to show you an example over here of something else I made up, and then explain why this is, and then we'll simplify. So what this means is two groups of x and 3. So this, what's in the parentheses, is what is in the group. And this out here is how many groups. And let me explain that with just regular numbers. Okay, so let's say I had something like this, 2 times 3. So that's saying two groups of 3. So if I had 3, there's one group, and then 3 again, there's another group. I've got 2 groups of 3 simplifies to 6. Now, again, it's the same idea as what's in parentheses is in the group. What's outside of the parentheses is how many groups we have. So as you can kind of see with my little simple example here is that when I'm saying 2 groups of 3, it's 6. What that's really doing is multiplying. So when we're doing groups of something, we're multiplying. So over here, what I would be doing is 2 groups of x, so 2 times x, and then I would also be doing 2 groups of 3. This time we have groups of more than one thing, so 6. The shortcut to that is multiplying, because of course if you go to think of this and you try to think, well, okay, that means I have -2 groups of x minus 3. That's a little bit tougher to wrap your brain around. What does negative 2 groups mean? The other way you can think about it is the opposite of 2 groups. So if I did 2 groups of x and negative 3, then I would do the opposite of that. But I show you this over here on the left just to show you that when you're doing groups of something, you're really multiplying. And so we can apply this idea to something that is maybe a little bit more fuzzy and harder to picture when we are working with something like negative numbers. So that's what we do. When we see these parentheses, we multiply because we're doing groups. So the first thing I'm going to do whenever I simplify an expression is distribute. This is called the distributive property, by the way, over here, distributive property. And so that's the first thing that we're going to do is the distributive property. So multiply, so negative 2 times x is going to be negative 2x. And I've got negative 2 times negative 3, which gives me positive 6. So I'm just going to write plus 6. I'm going to do the same over here because I have some more distributive property. So I've got 4 times negative 2x. I get negative 8x. So I'm going to just write minus 8x. And then I have 4 times 8, which gives me 32. Now at this point, I want to combine like terms. And because of time on the show, I'm not going to really in-depth explain this. But what makes something like terms is if it has the same variables and powers. So if you look over here, I've got a negative 2x, and I have a negative 8x. Those are the 2 terms I have that have the same variable. So we're going to put those together to give us negative 10x. And then I've got a positive 6 and a positive 32 that I'm also going to put together, which is going to give me positive 38. So that would be my second step there, is to combine like terms. And at this point, there's really nothing else I can do at this point. There's nothing to combine or multiply or anything. So this is my simplest form. Ta-da! All right, does your thing work?
It does, but now we fortunately have to go to the trivia question probably because we're out of time.
All right.
But
are you
I
sure you
am
know the
saving
answer?
this.
Tomorrow we will do it.
Are you sure?
I'm saving this for next year.
Next year.
Next year. Okay.
Next season.
We'll do it tomorrow, yeah.
Find out next
All right.
season on
Derek,
Homework
thanks for
Help.
saving him with that trivia
I
question.
owe you one.
Of course. So again, the question is, what are the 2 top-selling spices in the world? And the answer is pepper is first and mustard is second. Pepper comes in many colors, green, black, red, and white, but all come from the same plant. The color is related to how ripe it is and how it has been processed.
Oh, that's why in the pepper shakers, you see all different, like green and brown and all the different
Oh,
colors.
yeah.
I see. Makes sense.
They have different kind of levels of like pepperiness too.
Pepperiness.
Did you know that pepper has been used in cooking for over 2,000 years?
That is pretty impressive.
Yeah,
I was going to
well,
say, in the Middle Ages, did you know that a man's wealth was measured by his stockpile of pepper?
Really, I actually was about to talk about that because apparently back in the day, only wealthy people could get pepper.
Yeah.
And it was so expensive and sought after that traders formed spice routes from India to Europe and would often fight over them.
Yeah, spices were such a big deal in the past in a way that today, it's like, oh, pepper, it's on every table and every diner, and what do I care about
Yeah.
pepper? But back in the day, it was a really big deal, you know, and even like a salary, like we all make salaries for our jobs, right? The word salary comes from the word salt, sal, and it was because back in the day, your salary was, in the Roman Empire, you were paid in blocks of salt, because salt was so valuable, because you can use it to preserve food, do all kinds of other things.
Yeah.
So salary literally is your payment in salt. That's what the word salary means.
That makes
Interesting,
a
huh?
lot of sense. A lot of connections just made
There you go.
Okay. Well, pepper also loses its flavor and aroma through evaporation, so you have to keep it in a
Yes, you want
airtight
to keep it in an
container.
airtight container.
If you are not keeping it airtight, you know what? That's the thing I'm doing wrong.
Airtight
Anyway.
container.
Becca has just come to so many realizations in the last 2 minutes.
Mind blown.
Okay, yes. All right, well, we have to say goodbye. We will be back again tomorrow on Wednesday from 4:30 to 5:30 again to answer your questions and the one that Nathan missed today.
Yeah, answer my
So
question
we'll get
too.
that one. See you tomorrow.